with 2 radical 6, which again converges. Now, these will look like horrible questions, but it's actually just trick questions based off that, and you'll see why. Okay. All right. So again, hopefully you noticed, right? This is kind of like C, where there's a value that doesn't work, and that's when x equals 3, right? That can't be it. So we already have a template we're about to do. So it's going to look like this. So we're going to do the exact same thing we did for part A, just a little lengthier, right? So it's not too difficult, right? It's just tedious work and lots of work when it comes to it, okay? And now we just take the limit as both of them and just take each one's integral itself. So hopefully you guys notice here, I'll just do one of them. Let u equal x minus 3. Therefore, this is 1 dx, right? So this is the integral of 1 over u, which is natural log, right? So this ends up being the limit as t goes to 3 on the left of natural log of x, valued at 1 and t, and the same thing on the other side. Okay. Right, so now evaluate each one individually. So plug in t, this is limit as t goes to 3 from the left of natural log of, sorry, this is x minus 3 here. X minus 3. So t minus 3. And if you plug in 1, that's just gone, right? So all that's gone there. Plus natural log of 6 minus 3 is 3, minus natural log of t minus 3. All right, so as 3 goes to t on the left-hand side, so it goes like 2.9, 2.99, close to 3. So natural log of 0 doesn't exist, right? So that's gone. Over here, natural log of 3 does exist, so that's good. And as t goes to 3 from the right, so 3.11, 3.10001, again, plug in 3. Also, that goes right. Natural log of 0 doesn't exist itself. So we get natural log of 3 is the answer, which again converges. Okay. So far, so good. And now last one over here. So same situation we actually have here. I gave you guys a hint, right? So 0 doesn't exist in here, right? So that's where big no-no. So this is integral from t to 3 of natural log of x. Okay. And we actually did natural log earlier in the class, on the course when it came to it. I'll just quickly do it again just to verify, but so let u equal 1 of x, du equals 1 over x, dv equals dx, and v equals x. So this is going to be the integral of, actually v du, so x, natural log of x, minus integral of vx, so it's just 1 dx, right? That times that. Okay. So this ends up being x, natural log of x minus x. We evaluated both at t and 3. Okay. So you take the limit as t goes to 0 from the positive, and plug it in. So this is going to be 3t3 minus, I'll put this in big old thing, minus t natural log of t minus 3 plus t. All right, so as this goes to 0, that's gone, that's gone. So we're left with natural log of 3 minus 3. And there we go. All right, and the last thing in this section is something called the comparison test. So you guys are going to love this, but it's not too bad. So the comparison test is, let's suppose the stuff we just did above does not work, right? That's the worst thing, right? What if it doesn't work? Therefore, what else can do? So the comparison says, suppose that f and g are continuous functions where f of x is greater than g of x. So one function is strictly greater than or equal to the big one, okay, when it comes to it, for all x greater than a. So again, going back over here, so if the big one, so if the integral from a to infinity of x converges, so if this one converges using the same properties we just above, therefore by default, so does the one that's less than it. Okay. On the other hand, if the smaller one diverges, therefore the big one also diverges. Okay. So what we're going to do with comparing is we're going to figure, okay, given a function, we're going to see a function that's bigger than it or a function that's smaller, and then do one of these scenarios. Okay. So now it's going to be a little confusing. We're going to try our best to do this example as smooth as possible, and then figure out how in the world you find a g or an f or g such that you could do that. Okay. So we want to do this one. We use the comparison test to determine whether interval converges or diverges itself. Okay. So what we're going to do is, okay, we got to figure out a way how to evaluate this integral itself. All right. So we got to figure f of x or g of x such that it gets bigger. Now, the best thing I always do is just start from scratch. Okay. So we know that this is true, right? For sure. Okay. We know for that for sure. And again, this is like just seeing how we can do from, because essentially, right, we want one side equal exactly that, and we want to figure out something that's bigger or smaller to compare it to. So we're just going to, I'm just going to follow that template there. I know that's true. However, when I flip it, meaning when I bring it one over now, this now flips. Like that. And now finally, I'm going to multiply by x because I want exactly that on both sides, right? So this is going to be now x over x to the third plus 1, which is exactly what we started with. So multiply both sides by x. And notice this ends up being simplified to just 1 over x squared. So now we compared it. So let's just write this down real quick. So we have x over x to the third plus 1 is less than or equal to 1 over x squared. Okay. All right. So therefore, according to my definition, we found a function that is bigger than what we have, right? This is now bigger than what we have. So in our scenario, the g of x is what we're starting with, which is this. And we found something bigger, which is f of x. So therefore, if we can show that the bigger one converges, so does the smaller one. If this diverges, we have to go back to the drawing board because we don't know that. Okay? So we force ourselves to see, does this work, the first one work or not? If it doesn't work, we have to find something that's smaller than it and see if it goes backwards, or we just start from scratch. Okay? So we got to figure out, does the integral of, let's say, 1 to infinity of this work? Well, remember that little hint I told you guys about earlier? The integral that's going to help us a lot. P test. That's exactly what we have there. This converges if P is greater than 1. And in this case, P is greater than 1. P is 2. So therefore, this is a yes by the P interval. So therefore, the integral from 0 to infinity of what we started with, which was now smaller, right, than what we had, converges. Now, we don't know what it goes to, but again, sometimes it is literally impossible to find it. We just care about if it converges or diverges. So does it go to one number or doesn't it go to number? And again, this is when the comparison comes into play because we actually don't have to find it, unlike the other ones where we actually found where it converges to. These ones are just, we don't care what it goes to, we just know it does converge at some point in time. There you go.